In this video, we'll use random matrix theory to understand how PCA works. In the last two videos, we looked at the Marchenko-Pastur distribution, which describes the eigenvalue spectrum when the data is pure noise. This time we'll ask what happens when the data contains both signal and noise. We'll look at the SPECT covariance model, a simple but remarkably general model for high-dimensional data analysis. So the central question is, when can PCA distinguish signal from the noise? Random matrix theory gave us an exact threshold. And remarkably, the behavior is a phase transition. Below this threshold, the signal is not detectable from the noise by PCA, but above it, the signal suddenly becomes detectable. We'll first look at this phase transition in an example, then we'll derive the results. Okay, so let's get started. In the SPECT covariance model, the data matrix Y contains two parts, the signal part plus the noise part. In many modern data analysis problems, the matrix Y is very high dimensional. So let's say that the dimension of Y is P by N. So P is the number of features and N is the number of data points. Then the signal part of the matrix is usually in the form of a low rank matrix. And for simplicity in this video, we're just going to say that the signal part has rank 1, which means that U and V are both vectors. Then this parameter alpha is basically the signal strength. So it's a scalar. Then for the noise part, so X is a random matrix. And we can assume that the expectation of the entries X equals to 0, and then the variance of the entries equals to 1. Then this sigma parameter is also a scalar, and that controls for the noise strength. So this model is in fact very general in data analysis because this low-rank signal matrix can encode many different types of geometry. And for a very simple example, suppose the data contains two clusters that can be represented by the SPECT covariance model. So this axis is given by the direction u. And then for this particular example, we can think of the vector v as the cluster assignment. So v can be written as a vector contains +1 or -1. And these are the cluster labels. So let's say that this cluster is +1 and the other one is -1. So this vector v has dimension n, which is the same as the number of data points, and that tells us the cluster assignment. Then the centroid of these two clusters is given by the vector u. So these are the two centroids. And the position of this centroid is actually alpha times u. And the other centroid is minus alpha times u. Then the spread of the data points from this centroid is given by the noise part. Because the entries of X has mean 0 and variance 1, and the entries are ID, that is the reason why the data points spread around the centroid. And this parameter sigma here tells us the standard deviation of the noise. So this two clusters example is a way that we can visualize the SPECT covariance model in a very simple way. And the key question we can ask is, can we detect signal from the noise using PCA? So what we are really hoping for is that the PC1 can tell apart the two clusters. And a very natural question we must consider is how strong the signal must be for us to detect these two clusters from the PC1. And this question can be answered by random matrix theory. But before we even derive the result using RMT, we can get some intuition just looking at the geometry of it. So the distance between the two cluster centroid is given by 2 times alpha. And here we're going to make one more assumption that the norm of u equals to 1. So u is a unit vector, and then alpha tells us like how far away these two clusters are from each other. So that is like the signal strength. And then for the noise part, the strength of the noise is given by the standard deviation of the data. That is in the order of 2 times sigma. If we have a case where alpha is much greater than sigma, then that means like our clusters are really far apart, and the variation and the noise part is very small. This is the case where it is detectable. And in contrast, if alpha is much smaller than sigma, this is a case of undetectable. Basically, we'll have the centroid of the two clusters lives very close to each other. And we cannot tell the two clusters apart. So the most interesting case is actually when alpha is in the same order as sigma. And it turns out that when they are in the same order, sometimes the two clusters are detectable and sometimes they are not. There's an exact threshold we can find given by RMT. Also in here, we can actually define a quantity, beta, as a signal-to-noise ratio. Beta equals to alpha divide sigma. So that is a signal-to-noise ratio. Or SNR. So this is a key quantity we'll look at. And then the detectability threshold, let's call that beta C, is in the order of 1. So this quantity cannot depend on N over P. Otherwise, it will be just too small or too large. So this is the case when alpha and sigma are in the same order. Okay, so next, let's look at an example of how does change in beta affect the detectability of these two cluster examples. I generated a simulation of the two cluster data using the SPECT model we just introduced. On the left, we can see how well does the PCA separate the two clusters. And on the right, we can see the eigenvalue distribution of the sample covariance matrix. Then we can gradually increase beta, which is a signal-to-noise ratio. And we see that when beta is small, the PCA cannot really separate the two clusters. But if we keep increasing beta, the two clusters gradually become separable. I don't see that at the same time, the largest eigenvalue start to escape from the noise distribution. So the eigenvalue of the sample covariance matrix tell us the variance along the principal component directions. If we keep increasing beta, the variation in the principal component 1 start to become much larger than the bulk. So the first eigenvalue tells us the variance of PC1. And as we increase beta, it becomes a lot larger than the noise distribution for the eigenvalues, which describes the variance along other directions for the data. And very interestingly, the clusters become detectable around beta equals to 0.7. We see that below this threshold, the largest eigenvalue is the edge of the Marchenko Pastur distribution. And above it, an outlier eigenvalue start to separate from the bulk. And PCA can detect that as a signal. Actually, this beta threshold has to do with the dimension of the matrix. In this example, the dimension is 2000 features and 8000 data point, which means gamma equals to P over N equals to 0.25. And the threshold of the phase transition is actually given by beta C equals to gamma to the 1/4 power. Which equals to the square root of 0.5, which is approximately 0.7. This result is known as BBP phase transition, and we'll use random matrix theory to derive this threshold in the next part of the video. Okay, so now let's derive this result, aka the BBP phase transition. So we can start with the spect model, y equals to beta times uv transpose plus x. So let's say that the dimension of y is p by n. And we can define the parameter gamma equals to the ratio between p and n. So beta is a signal to noise ratio. And then u is a unit vector. V is our cluster assignment. And in here, just to be a little bit more general, you can just assume that the norm of V equals to n. So our binary assignment satisfies this. And the x is the noise part. You have the expected value of the entries equals to 0 and the variance equals to 1. And then the entries are IID. And in order to connect this with Marchenko Pastur distribution that we did, we need to look at the covariance matrix. So we'll have the sample covariance sigma hat equals to 1 over n times y transpose. The PCA depends on the eigenvalues of the sample covariance. We care about the first eigenvalue of the sigma hat. We hope that carries the signal part of the data. The first eigenvalue better stays outside the MP distribution. So let's denote that as lambda out. And we'll use the resolvent method to derive this equals to 1 plus beta square times 1 plus gamma over beta square. And this is the main result we'll derive in the next part of the video. And once we have that, the BBP transition is easy to obtain. So the phase transition basically occurs if we just compare this lambda out versus the edge of the MP distribution. So the edge of the MP distribution is given by, so let's say that is given by lambda plus equals to 1 plus the square root of gamma square. And the transition happens exactly at lambda out equals to lambda plus. So you can actually solve this equation real quick. We'll just have 1 plus beta square times 1 plus gamma over beta square equals to 1 plus square root of gamma square. And then we can just expand the terms. We'll have 1 plus beta square plus gamma over beta square plus gamma equals to 1 plus 2 times square root of gamma plus gamma. And then we can do some canceling. Then we have beta square minus 2 times square root of gamma plus gamma over beta square equals to 0. Then we basically have beta square minus the square root of gamma square equals to 0. And this gives us the exact threshold, which means beta equals to gamma to the 1/4. It means that the first eigenvalue, lambda 1, equals to the MP edge if beta is smaller or equals to gamma to the 1/4. And this eigenvalue becomes an outlier. That is something we can detect if beta is greater than gamma to the 1/4. And this gamma to the 1/4 is a threshold. This is the exact position we can detect signal from the noise. That is the entire statement of the BBP transition. But we still need to derive this result in here. So this is the main target for the next part of the video. And once we derive that, we have already shown that the BBP threshold, the phase transition threshold, can be easily obtained when we compare that to the edge of the Marchenko Pastur distribution. Okay, so for the next part of the video, let's try to derive this equation. For this particular proof, we're going to use the resolvent again. So the key idea here is that we want to separate out one particular eigenvalue of sigma hat from all the other eigenvalues. And this particular eigenvalue has to do with the specs. So this lambda out is associated with the signal matrix, which is rank 1. So this proof takes 2 steps. And the first step is whitening, or a standardization. So the idea is that we want to transform the matrix Y into matrix Z such that the covariance of Z equals to identity. Okay, so in order to do this, let's just first take a look at the covariance of Y, because that does not equal to identity matrix. So we can start with the spec model again. We have Y equals to beta times UV transpose plus X. Then the sample covariance matrix of Y, we can call that sigma hat. So that equals to 1 over n times Y transpose. So that equals to 1 over n beta UV transpose plus X times beta VU transpose plus X transpose. Okay, so after the expansion, we have 4 terms. Then we can also take the population covariance. So sigma, so that is the expected value of the sample covariance, which will simplify. So we'll just have 1 over n, and then for the first term, actually V transpose V equals to n. So we'll just have beta square U times n times U transpose plus beta times the expected value of x, and then VU transpose plus beta times UV transpose expected value of x transpose plus the expected value of XX transpose. So the reason we can simplify is because x is centered. So the expected value of x equals to 0, and then the covariance equals to n times identity. So basically this term, these two terms goes away, and this becomes n times identity. And we have beta square UU transpose plus identity. So the transformation from Y to Z is actually very straightforward. So we can just define Z equals to sigma to the negative half times Y. Then if we take the covariance of Z, we have 1 over n expected value of ZZ transpose. So that just equals to 1 over n times the expected value of sigma minus half Y transpose sigma to the minus half. Then that equals to 1 over n sigma to the minus half expected value of Y transpose sigma to the minus half. And then basically this part is a covariance of Y, which equals to sigma, right? Then this entire thing become identity. So, so this matrix Z has better properties than Y. The reason is because the entries of Z has expected value of 0, and then the variance equals to 1. Then the entries are also independent. Okay, so these properties makes matrix Z easier to analyze comparing to Y. But now we still need one bridge, because our main interest is the eigenvalue of the sample covariance for the sigma hat. So in order to build a bridge, we can actually look at the sample covariance of Z. So we can define the sample covariance of Z as Q hat. So that equals to 1 over n times ZZ transpose. And that equals to 1 over n times sigma minus half times Y transpose sigma to the minus half. And we can combine this part to get the sample covariance for Y. So that become sigma to the minus half sigma hat times sigma to the minus half. So, so since we are interested in the eigenvalue of this matrix sigma hat, so we can actually construct a similar matrix. So we can just multiply Q hat with sigma, and then we'll have Q hat times sigma equals to sigma to the minus half sigma hat sigma half. So now these two matrices has the same eigenvalue because they are similar matrices. And just for a quick recall that similar matrix has this form, as A equals to S inverse B times S. So A and B will have the same eigenvalues. And we can see that by basically diagonalizing the matrix B as S inverse, let's say that it's called U inverse lambda U times S. And then if we combine these matrices together, we see that A and B have the same eigenvalues, lambda. So all of that just means if we want to analyze the eigenvalues, the spectrum of the sigma hat, you can just analyze Q hat times sigma. They have the same eigenvalues. So the reason we want to do this is because sigma has two parts. So it has the spec part, and that is our main interest. Okay, so now we can move on to the step 2 of this proof. The second step is that we want to apply the determinant lemma. Which can directly give us an equation of that outlier eigenvalue. Okay, so let's do that. So our main target of interest is this lambda out. And the property of the determinant says that if we take the determinant of lambda out times I minus sigma hat, so that equals to 0. And because of the relationship we just derived, the determinant of lambda out times identity minus Q hat times sigma equals to 0. And we can expand the sigma matrix. So determinant lambda out identity minus Q hat times beta UU transpose. Okay, let me just change the order a little bit. So we have beta times Q hat and minus Q hat. So that equals to 0. Okay, now if you look at this determinant, it has a form of a full rank matrix perturbed by a rank 1 matrix. Okay, so now for the next step, we want to use the determinant lemma. So we can actually show the result real quick using the property of the determinant. So recall that for the property of the determinant, so let's say that you have two matrices A and B multiplied together. So that equals to the determinant of A times the determinant of B. But for this property to hold, we need both A and B to be square matrices. Okay, but when A and B are not square matrices, so this identity become a little bit different. So we'll just have determinant of identity plus A times B equals to the determinant of identity plus B times A. This is when A and B are rectangular. And applying this equation, we can actually derive a property of the determinant related to the perturbation by a rank 1 matrix. So, so the property is that, so the determinant of, let's say, a matrix M plus UV transpose, so that equals to determinant of M times identity plus M inverse UV transpose. Basically, in here, we use the first property. And then now we can use the second property to change the order for the second term. So that becomes the determinant of identity plus V transpose M inverse U. And because this second term is a scalar, so that just equals to the determinant of M times 1 plus V transpose M inverse U. Okay, so that is a property we're going to use. This is a determinant lemma. Okay, so let's continue. Let me just clear out this space. Move all these equations to the other side. Okay, so now we just need to combine a little bit terms in here, and so basically our basically this part will be M. Then you have beta times Q hat times U that correspond to the U in this equation. The M is in here, and then basically this U become V transpose. Okay, so now we just directly apply this lemma. We have the determinant of lambda out times identity minus Q hat times 1 minus U transpose, and then we have lambda out I minus Q hat inverse. Okay, let me move the beta to here. Then we have Q hat times U. So that equals to 0. Okay, good. So now if we look at the first term, so this term cannot equal to 0. The reason is because we have standardized the data matrix Z. So basically the eigenvalues of Q hat follows the Marchenko Pastur distribution. And the lambda out is basically outside this distribution. So that means the first term cannot equal to 0. So this just gave us an equation. So you have 1 minus beta times U transpose times lambda out times I minus Q hat inverse times Q hat U equals to 0. So now looking at this equation, we notice this part is actually the resolvent of Q hat, and Q hat is the sample covariance of Z. And we better take advantage of this. Okay, I think I made a mistake in here. The beta should be beta squared. Okay, this should be squared, and this beta should be squared. Yeah, that's better. Okay, so now we just need a little bit manipulation. Okay, so basically we'll have 1 equals to beta square U transpose lambda out identity minus Q hat inverse. Then we can do this. You can use lambda out times identity minus lambda out I minus Q hat times U. Then we'll have 1 equals to beta square U transpose. And then just gonna copy this. Then we have minus beta square U transpose. Basically, these two can cancel. right? And so we'll have U transpose U. Okay, good. This is very nice. And remember that we derived before. So this part, this quadratic form, so that just approximately the trace. So it's 1 over P times the trace of lambda out minus Q hat inverse, which equals to the Stieltjes transformation M of lambda out. Okay, this is nice. And for U transpose U, that just equals to 1. So we'll just have beta squared times M of lambda out times lambda out minus beta squared equals to 1. Okay, very nice. So we'll just have M of lambda out equals to 1 plus beta squared over beta squared times lambda out. And now we can just plug this to the equation that we derived before for the Stieltjes transformation. So equation is gamma times lambda out times M squared minus lambda out plus gamma minus 1 times M plus 1 equals to 0. Okay, so now we can just swap out M for the equation with respect to beta. We'll just have gamma times and then lambda out times 1 plus beta square beta to the 4th lambda out minus lambda out plus gamma minus 1 times 1 plus beta square lambda out plus 1 equals to 0. I think we have a square in here. Okay, so this can cancel. Okay, now all we have to do are just some basic algebra. Okay, we can fast forward this part. Then for this part, we can factor out 1 plus beta square over beta square. Then you have gamma times 1 plus beta square over beta square minus gamma plus 1. And for this part, it becomes, we have gamma over beta square plus gamma then minus gamma plus 1. Then gamma can cancel. And then we can just move the terms around. We'll have lambda out equals to 1 plus beta square times gamma over beta square plus 1. Okay, so after some algebra, we have, I think we have derived the correct equation for the eigenvalue. And basically, after we have the form of the eigenvalue, we can show the phase transition by just comparing this eigenvalue outlier with the edge of the Marchenko-Pastur distribution. And that gave us the threshold of beta equals to gamma to the 1/4 power, which is where the phase transition happens. So below this threshold, we can already detect the signal using PCA. But after that, this eigenvalue will become the outlier. And that's when the signal shows up if we plot the data using our principal component analysis. Okay, good. So that's pretty much about this video. Comparing to the previous few videos, this derivation feels pretty straightforward. So next time, we are going to look at universality. So a very remarkable thing is that the behavior does not require data to be Gaussian distributed. And so even for our SPECT model and the derivation of the Marchenko-Pastur distribution and the Wigner semicircle law, we didn't really assume the data to be Gaussian, right? We only require the mean and variance. So next time we are going to talk about universality. It's a remarkable fact that under some mild conditions, many non-Gaussian random matrices have the same limiting eigenvalues as the Gaussian matrices. For all of the results we have looked at so far, the Wigner semicircle, the Marchenko-Pastur distribution, and the BBP phase transition, it does not depend on the entries being Gaussianly distributed. And universality is the reason why random matrix theory is very useful for real-world data. And it shows why principal component analysis is so useful even for the non-Gaussian data, because the spectral behavior does not require the data itself to be Gaussian.